All right. I know the notes portion of the video was pretty long, so let's just dive right in here and talk about some ideal gas problems. Okay, so the first one, these are all from chapter 5, by the way. First one is number 47. An aerosol can contains 400 milliliters of compressed gas at 5.2 atmospheres of pressure. When all of the gas is sprayed into a large plastic bag, the bag inflates to a volume of 2.14 liters. What is the pressure of the gas in the plastic bag? So they give us an initial volume and pressure. Okay, we're then spraying all of the gas into a larger container, right? 2.14 liters compared to 0.4 liters or 400 milliliters. We have to calculate the new pressure of the bag. Okay, assume a constant temperature. Now, we could use the ideal gas law. Okay. But actually, if we only have pressures and volumes, then Boyle's law is sufficient. Okay, and remember that Boyle's law, Charles' law, and Avogadro's law were sort of combined together to give us this ideal gas law. So the same fundamentals are still there, okay? And it makes sense actually, right? Because if we consider the ideal gas law here, if the temperature is constant between the two situations, and the number of moles of gas, right, we're spraying the entire container from one place to another, the amount of gas is staying constant, then this entire right side of the equation is staying constant. There's no change. So the only thing that's changing is the pressure and volume. And that's what is Boyle's law is talking about, right? Is when you have everything on the right side of the equation being constant, the pressure and volume, the product of these two has to remain constant. So we're actually just going to use this Boyle's law equation. P1 V1 equals P2 V2. All right, so let's set that up then. All right, so P1 V1 is equal to P2 V2. My initial conditions were volume of 400 milliliters. Let's just convert that to 0.4 liters, okay? And my initial pressure was 5.20 atmospheres, fairly compressed, right? Roughly 5 times that of atmospheric pressure. Okay, and so we're taking all of this gas and spraying it into a new, larger volume, which they give us, 2.14 liters. And the question is, right, what is that new pressure? Okay, and it really is as simple as it looks. We're just going to solve this equation for P2, okay? And in fact, what I'm going to do is I'm going to actually solve for P2 ahead of time, right? If I divide both sides of the equation by V2, then P2 is equal to P1 V1 over V2, okay? And so this is going to be 5.20 atmospheres times 0.4 liters divided by 2.14 liters. Notice how the units here will cancel, and so you end up with units of atmospheres, right? And so my answer, if I get my calculator out here, 5.2 times 0.4 divided by 2.14. Okay, now before I give you the answer, let's think about this, okay? We're going from a small volume and a high pressure to a larger volume, okay? Should we expect the pressure to go up or down? Right? We're taking a certain amount of gas at a constant temperature with these conditions, right? About half of a liter at 5 atmospheres. If we allow that gas to expand into a larger volume, we should expect the pressure to go down, right? You're spraying the gas from a condensed or from a compressed can into a larger volume. We would expect that pressure to come down, and in fact it does. Okay. Let me give 3 significant figures here since it looks like our other starting numbers here. I think that was 400.0 there. I think all these have 3 sig figs. So this is my final answer here. Okay, my pressure has come down. Okay. All right. Let's go look at the next problem. Once again, chapter 5, number 53. Suppose 2 200-liter tanks are to be filled separately with the gases helium and hydrogen. What mass of each gas is needed to produce a pressure of 2.70 atmospheres in its respective tank at 24 degrees C. Okay, so here we have volume, pressure, and temperature, and we don't have like a comparison of two different states. We're not going from one state to another. This is just asking us, hey, you got these two tanks, we're trying to fill them up. How much of each gas do we need to fill them up to these certain specifications? So this is a good example of where we're just going to use the ideal gas law straight away. We have the pressure, volume, and temperature. We're going to be solving for N, which is number of moles, okay? And then in order to figure out the mass, we're going to need to do some converting using molar mass, okay? So let me go ahead and write down the initial things that the problem gives me, okay? So the volume is 200 liters. The pressure, 2.70 atmospheres, and the temperature is 24 degrees Celsius. Okay, now I mentioned in the video that I was going to talk a little bit about temperature and the units of temperature. Let me show you something here. Okay, on this formula sheet, okay, which is the same formula sheet you get to use on the AP exam, anytime you use the ideal gas law, okay, PV is equal to nRT, that value R is the gas constant. Okay, and look at the units for the gas constant. Okay, all of the temperature units here are in Kelvin. Okay, there's no degrees Celsius here. Anytime you're using temperature in an ideal gas situation, you need to convert your degrees Celsius to Kelvin. Okay, and it's actually super easy. They give you the formula here. The Kelvin temperature is going to be equal to your degrees Celsius temperature plus 273. Okay? What that means is that 0 Kelvin, that's absolute zero. That would be negative 273 Celsius. So like negative 273 Celsius is like the coldest anything can get, and it goes up from there. Okay? Kelvin is like an absolute temperature because it starts at 0. You can't have negative Kelvin. That's why it's used in these equations here, because like you can understand like having a negative temperature would really cause your calculations to get a little bit wonky, right? So we're going to do 24 plus 273. Some quick math here tells me that this is equal to 297. Okay? K. By the way, it's not degrees K, it's just K. Okay, there's no degrees Kelvin, it's just Kelvin. All right? So this is the temperature that I'm going to want to use. All right, and my ideal gas law is PV is equal to nRT. Okay, so let me go ahead and plug in some values. Right, I said we're going to be solving for N, right, because we have pressure, volume, temperature. We actually are going to know the gas constant as well. They're on this paper. We'll bring that back here in just a second. I'm going to go ahead and solve for N ahead of time. Okay, so N is equal to PV over RT. Okay, let me go ahead and plug in my values now. So 2.70 atmospheres for my pressure, 200 liters for my volume. Okay, I know that my temperature is 297 Kelvin. All right, so what goes here? That's the gas constant, okay, R. And look at the units here. Atmospheres, liters, and Kelvin. So we want to pick the value of R that has atmospheres, liters, and Kelvin in it. All right? That would be the second one. Atmospheres, liters, Kelvin. Okay? 0.08206. I'm not going to write all those units. Actually, here, I will. I'll show you how it works. Okay, kind of had to squeeze those in there. So you can see here how the units work. We have liters in the numerator, and then liters in the numerator of the denominator, which means it's just in the denominator. Same thing with the atmospheres. Kelvin in the denominator, and then Kelvin in the denominator of the denominator, which means it's actually in the numerator, so the Kelvins cancel. And I've got moles in the denominator of the denominator, which means it's actually in the numerator, which means I'm going to get moles for my value of N. Okay, so the units are a little bit weird here, but it does work out. So my value of n then is, I'm going to get my calculator out again, 2.70 times 200 divided by 0.08206 and 297. N is equal to 22 points. Let's see, how many sig figs should I work with here? It looks like 3 is probably good enough. 22.2, okay, moles. All right, that's how many moles of substance I need to fill these tanks. Now, if I bring back the problem, right, it said we have 2 tanks, each one to be filled separately with helium and hydrogen, and we want to know the mass of each gas. Well, here's the thing. It's going to be the same number of moles in each case. Okay, so I have 2 different tanks, one for helium, one for hydrogen. It's going to be this number of moles in each case. The only difference here is that these have different molar masses, right? So let's just do one of them, for example. All right, so for the helium tank, I have 22.2 moles. To figure out how much mass of helium I'm going to need, I need to multiply by the molar mass of helium, which is, I believe, 4.003, or maybe just 4.00, depending on the periodic table. Okay, 4.00 looks like. 4.00 grams of helium per 1 mole of helium. Okay, I'm getting that from the periodic table. All right. So this is 88.6 grams of helium. Okay, and then to do it for hydrogen, it would be the same process. You would just use the molar mass of hydrogen instead. Okay, so important concept here. It's the number of moles that's constant here. The mass would be different. So this tank would actually weigh more than this one, despite having the same other properties. They'd have the same volume, pressure, temperature, and number of particles, but they would have different masses, okay, due to those molar masses. Okay, all right, and then let's pull up the last problem here, number 59, once again from chapter 5. A typical adult inhales 450 milliliters of air in any one breath. How many air particles are in a typical breath at 745 torr and 22 degrees Celsius? Okay, once again, we have a volume, pressure, and temperature. So we're probably going to need to use the entire ideal gas law. It's asking us how many air particles there are in a typical breath. So you'll remember that Avogadro's number is particles per mole, right? 6.022 times 10 to the 23rd particles per mole. So if we can use the ideal gas law to solve for n, the number of moles, then we can use that number of moles to figure out how many particles there would be, right? So kind of similar to the last problem, instead of going from moles to mass, we're going to go from moles to number of particles, okay? So let's go ahead and write down the information we have to start with here. Our volume is 450 milliliters. Let me go ahead and convert that to liters, okay? Probably a good step, good first step for each problem. If you have milliliters, go ahead and convert it to liters, okay? Let's see, my pressure is 745 torr. Remember, that's the same as millimeters of mercury. And then my temperature is 22 degrees Celsius. I'm going to convert that to Kelvin, right? So 273 plus that value. What is this? This is going to be 295 Kelvin. Okay? All right. So my ideal gas law, PV is equal to nRT. I know my pressure, I know my volume, I know my temperature, and R is going to be a constant. Solving for N, let me go ahead and do that up front. Same exact situation as last time. N is equal to PV over RT. Okay, my pressure, 745 torr, times my volume, 0.45 liters. Okay, divided by R, we'll come back to that in a second. 295 is my temperature, 295 Kelvin. All right, let's consult our list here. We're looking for a value of R that's using these units, torr, liters, Kelvin. Okay, well, here it is, torr, liter, Kelvin, bit of a different value, okay, 62.36. Okay, there's the units. Okay, once again, these units do cancel out. Liters in the numerator, liters in the numerator of the denominator. Same thing with torr, and then Kelvin. Okay, so I'm going to be left with moles. All right, so N is equal to 745 times 0.45. That's a 0. Divided by 62.36 and 295. Okay, doesn't look like a large number of moles here. 0.018 moles. Okay, so this is the number of moles of gas that I have here. Now, this is interesting. If this was like the previous problem, where we were trying to convert this to mass, we would be in trouble, okay? Because when we breathe in air, air is actually made of several different things. It's made of nitrogen, oxygen, a little bit of water vapor, some carbon dioxide, argon, other trace amounts of things like methane, etc. So that would be difficult because we don't have a single molar mass that we could use. Good news for us is that we're supposed to be solving for number of particles, okay? And so we can just use Avogadro's number, 6.022 times 10 to the 23rd particles per 1 mole. This value here is going to tell us, well, in conjunction with our starting number of moles, how many particles we are breathing in, okay? So we're going to take that starting number of moles, multiply it by Avogadro's number, right? We want these units to cancel, right? And this is going to give us our number of particles. Okay, so let me do this in my calculator real quick. Okay, we get a total of 1.10, okay, with some rounding there, times 10 to the 22nd particles. Okay, so you're breathing in this many particles of air, okay? And let's say you did want to figure out how many nitrogen molecules you were breathing in compared to oxygen. Well, you could use the percentages, right? So air is approximately, 79% nitrogen, approximately 20% oxygen, approximately 1% argon, and trace amounts of other things, okay? You could then multiply, the decimal versions of these percentages by that number there, and you could figure out how much of each individual particle, right, that you had. Okay, but this right here is your overall answer there. Okay, all right. So those are just three examples of some types of problems that you can do. The problems are going to be, all over the place. What you have to recognize is, what information am I given to start? What am I looking for? What equation can I use, or how can I set up the equations that I have at my disposal to solve for the missing thing? Okay, and a lot of times using pictures, diagrams, writing everything out and sort of taking it all in, rather than just staring at a sentence, right? Writing things out on your own piece of paper and sort of trying to imagine the scenario in your head. All of those things combined can make the process a little bit easier and manageable, make you a good problem solver. So we'll obviously do some more practice with this in class, but there you go. Okay, thanks a lot. See you in class.